Hello students, welcome to the class. So today we'll do the theory part 11 of the NCERT chapter 9 hydrocarbon, in which we will cover the NCERT section 9.3.5. So this is our disclaimer. Now our today's objective would be to learn about alkenes. So we are doing this objective of distinguishing your alkanes, alkenes, alkynes and aromatic compound on the basis of their physical and chemical properties. So first let us continue with this alkenes. We have already dealt with the physical and chemical properties of alkanes. Now, if I talk about the specific names of the NCERT section that we are going to cover, then it is 9.3.4 properties of alkenes, and then after we will just end our lecture with a short summary. So let's start with the physical properties of alkenes. Now, alkenes have similar physical properties to alkanes except the types of isomerism they show. So this is one of the key difference which is shown by the alkenes, and alkenes can show geometrical isomerism, which means the same molecular formula can have different arrangement of atom in space due to the double bond. For example, you can have cis and trans forms where groups are on the same side or opposite side of the double bond. Another difference is there in their polarity. So alkenes have slightly higher polarity compared to the alkanes. This is because the double bond in alkenes creates a region of higher electron density, making a molecule bit polar. However, they are still mostly non-polar overall. What about their physical appearances? So they are colorless and odorless at the same time. Now, due to their overall non-polar nature, they are mostly insoluble in water, whereas if you consider their solubility in non-polar solvents such as benzene, then in that case they are superb in their solubility. For example, can we take an example? Yes, so we have ethene here. It is a colorless gas and has a faint sweet smell, and ethene is not perfectly soluble in water due to its non-polar nature. Now, we will try to study the properties, or I would say the physical properties of alkenes with the help of van der Waals force. So what is the effect of van der Waals force on the alkenes physical properties? Now, first of all, you should know that van der Waals force increases with increasing molecular mass. So the first factor is molecular mass. As the molecular mass of an alkene increases, the van der Waals force between its molecules also gets stronger. This is because larger molecules have more electrons, which leads to stronger temporary attraction between them. Next, increasing surface area will lead to result in a stronger van der Waals force of attraction. Coming on to the physical state of alkenes, as we move from smaller to larger alkenes, their physical state changes from gas to liquid to solid. This is because the increasing molecular mass and surface area makes the van der Waals forces stronger. So, the molecules stick together more tightly. So, as the molecular mass of the alkene increases, what happens? What we said is that the van der Waals force also increases. This means higher alkenes need more energy to separate their molecule, which is why they are found as liquid or solid rather than gases. For example, the first three members of the alkene series, which is ethene, propene, and butene, they are all gases at room temperature. Their molecules are small, so the van der Waals forces between them are weak and they don't stick together very well, resulting to the gaseous state. Then after 14 alkenes, the next 14 alkenes which have a longer carbon chain are liquids. Their larger molecular mass and greater surface area means stronger van der Waals forces, right? So the molecules are held together more tightly than in the gases, right? And lastly, the upcoming higher alkenes are solid in their physical state due to their higher molecular mass. So this was all about the physical properties of alkenes. Now we will move on to the chemical properties of alkenes. In comparison to the alkenes are more reactive. Okay, so they are more vulnerable to reactions as compared to the alkanes. Why is it there? Because they have electron rich pi bonds, which increases their reactivity. So pi bonds are a type of covalent bond. So as you know, formed by the side-on overlap of the atomic orbital, and they make the molecule more attractive to certain reactants. Now this loosely bounded pi electrons are held less strongly, okay? And due to this pi electron, which are less tightly bounded, they can be more easily attacked by other chemical reagents, making alkenes more reactive. Got it? Now they show electrophilic addition reaction due to this pi electron. So you know it, if they are electron rich, means they will attract electron loving species towards them. And as a result of this attraction, they show electrophilic addition reaction. Apart from this electrophilic addition reaction, they may also undergo some other specific reactions like oxidation, which is basically, I would say, the increase increase in oxidation number. Next we have ozonolysis, which is the reaction with O3 or ozone, and lastly the free radical substitution, which is under special condition. So we will talk about each of this one by one. Okay, starting with, so what we will do is we will divide our whole set of reaction of alkenes into two parts. The first one is electrophilic addition reaction. So this electrophilic addition reaction involves addition of dihydrogen to an alkene. So this process is called as hydrogenation. Next we have addition of halogen, which is represented by X2, and X can be chlorine, bromine or iodine. After that we have addition of hydrogen halides. So here hydrogen halide is represented by HX, where X is a halogen like chlorine or bromine. Further, we can also have addition for sulfuric acid. Then we have addition of water. Since water is added, we can also call it as hydration. Got it? Now this addition of water occurs in the presence of an acid, which act as a catalyst there, mainly to form alcohol. Now these are the first set of reaction, and we have some another set of reaction which are specific. First one is oxidation, which is basically the increase in oxidation number of carbon. Then we have ozonolysis, which is reaction with O3 or ozone. And lastly, we have polymerization, where certain single units combine to form a bigger unit. Got it? So let's start with this first electrophilic addition reaction, which is addition of dihydrogen or H2. Now here, in this reaction, alkenes react with hydrogen gas in the presence of a metal catalyst such as nickel, palladium or platinum. Try to remember the names of all these three metals, okay? Don't stick to one, so that can be harmful in your answering part. The catalyst helps break down the hydrogen molecule and allows the hydrogen atom to add across the double bond, turning your alkene to an alkane. Now here is a specific reaction for it. So we are adding H2 to ethene, and this addition of hydrogen, dihydrogen, can occur in the presence of platinum, palladium and nickel, shown by oblique. And after this addition of hydrogen, the ethene is converted to ethane. Remember, all of them are present in their gaseous states. Got it? Moving on further, next we have addition of halogen, which can be chlorine or bromine, represented as X2. Notice how halogens such as bromine or chlorine can add across the double bond of an alkene. This reaction forms what we call vicinal dihalide, meaning two halogen atoms end up attached to adjacent or neighboring carbon atoms. So this is a classical example of an electrophilic addition reaction. For example, if we are adding Br2 to ethene, here we can see on the reaction of ethene with bromine, it gives us 1,2-dibromoethane. So what we can say, that your formed product is a vicinal dihalide because the bromine is just present on adjacent carbon. Now this reaction has an important application. It can be used to test unsaturation in an organic compound. If you add bromine water, which is reddish orange, to an alkene, the color disappears. The reddish orange color disappears. This loss of color tells us that a double bond was present, confirming unsaturation in the molecule. Now, addition occurs across the double bond in anti-fashion. Anti-fashion means they are added on the opposite phases of the double bond. If you consider ethene, suppose, so it is a planar molecule because each carbon is sp2 hybridized. Now, if it is a plane, it can have two sides. So basically, when two bromine atoms come, they are added on the opposite side. So if one is coming from the top, the other will come from the below. Now moving further to this addition of halogen, one very important point is here. So of course, it is an example of electrophilic addition reaction, but it involves the cyclic halonium ion formation. How it is represented? You can see here, this is your normal alkene. What will happen? So the pi electrons or the pi bond is being donated onto bromine. Got it? And in a cyclic type reaction, we get a cyclic halonium ion. Here we call it specifically as cyclic bromonium ion. See, the bromine has a positive sign and the other bromine is kicked out as Br minus or bromide ion. Now this Br minus will attack from the opposite side where your Br plus is present, and that results in anti-fashion addition. Okay. Now moving on further, next we have addition of hydrogen halides, which is represented by HX. So hydrogen halides such as HCl, HBr and HI react with alkene to form alkyl halides. An alkyl halide is simply a hydrocarbon where one hydrogen atom has been replaced by a halogen atom. For example, if we add HBr to ethene, we get bromoethane. What is the order of reactivity here? So hydrogen halide, so HI reacts fastest, then comes your HBr followed by HCl. This means that if you have three available halogens, HI will add quickly to the alkene. This order is due to the bond strength between hydrogen and the halogen. Weaker is the bond strength, easier is to break and react. You know it very well that the size of iodine is very large. Due to this, the bond length is larger as compared to HBr and HCl, and hence it can be easily broken. Further, just like when we add halogen to alkenes, adding hydrogen halide is also an example of electrophilic addition reaction. This means the alkene's double bond act as an electron-rich area that attracts the electrophile, which is the hydrogen atom in HX. This is a fundamental reaction type in organic chemistry. Now, we'll talk in detail about this addition of HBr because there are many possibilities for the product type. First, consider a symmetrical alkene like your ethene. When HBr adds to ethene, both carbon atom in the double bond are the same. Means the chemical environment around both carbon is same due to the symmetrical nature around the double bond. So it doesn't matter which carbon gets the hydrogen or the bromine, the product is also the same, making this reaction straightforward. But when we talk about unsymmetrical alkene, things are complicated as compared to symmetrical alkene. So we'll try to understand this thing and see which one is the preferred product. Now, starting with the addition of HBr to a symmetrical alkene. Now, symmetrical alkene, as I said, they have similar groups attached onto the double bond on the either side of the double bond. For example, in ethene, both carbons in the double bond have 2 hydrogens each. This symmetry affects the outcome of the reaction that we are dealing with, as we will see it in a moment. Addition of your HBr to symmetrical alkenes take place by electrophilic addition mechanism. How? So here is an example of that. Suppose you are taking ethene and reacting it with HBr, then it would give you only and only one product, which is but2ene. You can see here, if you add H on the left or on the right, it will give you the same product, which is but2ene. And same can be said about the addition reaction of HBr to but2ene. Here also, the double bond has same group on the either side. So the doubly bonded carbon on the right side has one H and one methyl group, whereas the doubly bonded carbon on the left hand side also has the same H and methyl group. No matter on which side you add H or Br, you will end up getting the same result. So what we can say, that single product is formed in both of these reactions. Now moving on further, we will try the addition onto an unsymmetrical alkene and see what happens here. So an addition of HBr to unsymmetrical alkene can result in two different possible products. For example, propene can react with HBr to form 2 bromopropane and 1 bromopropane. So these are the two possible products. Now the key question is that which product will be the major one. So this sets up to discuss how we predict the outcome using a specific rule. What is the first product that is possible? It is 2 bromopropane, and the second one is 1 bromopropane. How do you decide it? So the major product is predicted with the help of Markovnikov's rule, which we will see in the next slide. So let us study this Markovnikov's rule. Markovnikov rule predicts the major product in addition of alkenes. Which alkenes? Specifically unsymmetrical alkenes, where more than one product is possible for the same reaction. According to Markovnikov's rule, the negative part of the molecule that is being added attaches to the carbon atom that already has fewer hydrogen atoms. This is a key point to remember, as it helps us to decide the structure of the main product. Now we can take example. For example, we are taking HBr to propene. So you know it very well that your propane is an unsymmetrical alkene because both the groups are different across the double bond. The second number carbon has 1 H and 1 methyl, whereas the 1 number carbon has 2 H. Therefore, both of the carbon are not bearing the same group. Therefore, two products are possible here. It is seen that the primary carbocation forming product is much more stable as compared to is less stable as compared to the secondary carbocation. Okay, so what are we doing here is we are taking HBr with this given alkene, and due to this HBr, H plus is donated in the reaction mixture, and this H plus can add onto two carbons. If it is adding onto the second carbon, then it results in a primary carbocation which is less stable. Whereas if this H plus is added on the first carbon, it results in secondary carbocation which is more stable. Now moving on further, we got our next step intermediate for the further reaction, which is a secondary carbocation. So this secondary carbocation is more stable and hence it is formed in greater amount. This secondary carbocation is further attacked by the bromide ion to form 2 bromopropane as the major product. Okay, so bromide ion is acting as the nucleophile here. So what we can say that the obtained major product is 2 bromopropane. We can obtain minor product as major product using peroxide with HBr. So this is the second thing that we are going to study, and this is named as a special reaction named as anti-Markovnikov addition. Now can you apply the Markovnikov rule here? Yes, it's very obvious. You look, what is the negative part of your HBr? It is Br minus. The positive part is H plus. So the Br minus is going to that carbon which has lesser number of hydrogen, and that is absolutely your middle carbon. Therefore, it is getting your Br minus. Now moving on further. Now we will study the anti-Markovnikov addition, which is also studied under this Kharash effect. According to this, in the presence of peroxide, the addition of HBr to unsymmetrical alkenes occur opposite to that of the Markovnikov's rule. Instead, the reaction goes to the opposite way. Here, the peroxide acts as an initiator, starting a chain reaction that changes which atom attaches where. Now, the bromine atom attaches to the carbon with more hydrogen atoms. So this is just the opposite we saw in the previous case, because there the bromide ion was getting attached to that carbon which has lesser number of hydrogen. Here it is getting attached to that carbon which has more number of hydrogen. Therefore, we call it as anti-Markovnikov's rule because it is the opposite of the Markovnikov's addition. Let me take an example. Suppose we are taking the addition of HBr to propene. But what is the way to do it? I said it, you have to use the peroxide. What is the peroxide that is used here? It is your benzoyl peroxide. You can see it is C6H5 COO whole twice. So this whole thing is under 2, then O2. So this is your peroxide, and in the presence of this peroxide, your Br is getting added onto the last carbon. So here we are getting 1 bromopropane as the major product rather than 2 bromopropane, which was seen in the case of Markovnikov addition. Now this is a very important distinction which you should notice. So what we can say, peroxide effect is always observed with the HBr and not with HCl or HI. Now this is an important point to remember. You can get your anti-Markovnikov addition with the help of peroxide only with HBr and not your HCl or HI. Okay, remember this is very, very important for you. Moving on further, next we will see the mechanism of this anti-Markovnikov addition. So let's see how it is added. So peroxide effect proceeds via free radical chain mechanism. A free radical is a particle with an unpaired electron, making it highly reactive. This is different from the usual ionic mechanism we see in the addition reaction. The presence of peroxide is what triggers the radical pathway. What we do is we take your benzoyl peroxide and it is seen that your peroxide is breaking down into two parts, right? And these two parts are further dissociated as four parts. How it can be redeemed? So benzoyl peroxide is converted to a radical which is further converted to a phenyl radical and 2 moles of carbon dioxide. Okay. Now this whole reaction occurs in the presence of heat or UV light, which triggers the dissociation, the homolytic cleavage of this benzoyl peroxide. Further, your phenyl radical reacts with your HBr to form a benzene and a bromine radical. So this is your second step, which is under your initiation step for propagation step. The first step is the initiation, which is the formation of radical. The second step is propagation, where one radical is producing another radical. Moving on further with the mechanism. So what we can say, lastly, this again a propagation step where your bromine radical is reacting with your double bond to form two types of radical. Here the A radical is less stable because it is a primary free radical. Primary radicals are less stable because of the fact that they lack the stabilization due to inductive effect and hyperconjugation. Whereas again the secondary free radical is more stable. So this is very important to remember. This was seen in the case of Markovnikov rule as well. But there H plus was added in the first step. Therefore, we got the Markovnikov type of addition. Here bromine is getting added and the radical is formed. You can just analyze this keenly to get a much more appropriate version. Further, moving on with this Markovnikov addition mechanism, you know that your secondary free radical is more stable than a primary radical. So the 1 bromopropane is the major product. How does it end? So your radical form, the secondary radical form, reacts with HBr, which again results in homolysis of this HBr. And as a result of this, you get a bromine radical. Apart from the major product, you will also obtain the minor product. But since your primary radical is formed in a small amount due to the instability of the primary radical, we get the 2 bromopropane in a small amount, again creating a bromine radical along with it. Now, let us move on to another electrophilic addition reaction, which is addition of sulfuric acid. Now, remember, we will use this Markovnikov rule everywhere to represent the product side. It is seen that similar to the addition of HBr in the presence of a polar reagent, I would say a polar environment, here also the sulfuric acid is also added in the Markovnikov fashion. Means the negative part, which is O minus SO3H of the addendum, gets attached to that carbon which has lesser number of hydrogen. This is because again due to the formation of more stable carbocation intermediate. Here is an example of that. You can see ethene is getting added to H2SO4 is getting added to ethene to form ethyl hydrogen sulfate. Here we don't have to worry about the end product because it will be same due to the symmetrical nature of the alkene. Now this is used in the industrial preparation of alcohol. Okay, this process is used in the industrial preparation of alcohol. Let us move on further. So, we have seen a case of symmetrical alkene where the end product is not affected by Markovnikov or anti-Markovnikov rule. Then we have addition of water, which is also named as hydration. So, water is getting added to alkene to form the alcohol. For example, if we start with ethene and add water, we will get ethanol as the end product. This is a common way to make alcohols in the lab and industry. Now, in the presence of a few drops of concentrated sulfuric acid, what we do this reaction. So, basically, we are catalyzing the reaction with the help of an acid, which is your H2SO4. This makes the reaction faster. Again, this addition also follows the Markovnikov rule, means the negative part of your molecule. So, what will be the negative part of molecule of H2O? It will be OH minus. So, it has two parts, OH minus and H plus. So, the negative part will go onto that carbon which has a lesser number of hydrogen. For example, if you are adding your H2O to 2-methylpropene in the presence of H plus, which is acting as your catalyst, the OH part is going on to the which carbon? That carbon which has lesser number of hydrogen. So, you can see here in 2-methylpropene, one of the carbon has 0 hydrogen. Therefore, your OH is going there, because as your H plus is first added, which is your catalyst, it will result in that carbocation which is more stable, and obviously it is the tertiary one. You can just try out the mechanism by yourself. So, we have dealt with all of those electrophilic addition reaction. Now, we will move on to some specific reactions of alkenes. So, the first one is oxidation. What about oxidation? So, alkenes on reaction with cold dilute aqueous solution of potassium permanganate, which is also named as Bayer's reagent, it produces vicinal glycol. Here also, the vicinal means the two OH groups are present on adjacent carbon atoms. And what we are taking as a reagent, we are taking KMnO4. So, your potassium permanganate is KMnO4. Next, the hydroxylation occurs. So, we also name this reaction as hydroxylation, where the two OH group are added on adjacent carbon. Now, this oxidation process, which is specifically with KMnO4, is again used for the test of unsaturation, and we call therefore your potassium permanganate as Bayer's reagent. Previously, we have the test for unsaturation using the halogen, okay, X2, where your bromine water has a reddish color, which was further decolored due to addition of these two bromines across the alkene double bond. We can take an example. Suppose we are taking ethene. If we are adding the H2O in the presence of dilute KMnO4. So, why we are saying it with H2O? Because it is written in the question that your whole reaction is undergoing in the aqueous solution. It would result in vicinal glycols. You can see here very clearly that the two OH are added on adjacent carbon of the ethene. What will happen during this reaction? Of course, your color change will occur. Basically, your purple color of your potassium permanganate will be converted to brown precipitate of MnO2. So, your KMnO4 is getting reduced because it is oxidizing your alkene to glycol. Now, moving on further. In this oxidation reaction, next we have your acidic potassium permanganate or dichromate. Now, the great thing with this acidic potassium permanganate or dichromate is that it oxidizes your alkenes or ketones, okay, alkenes to ketones or even acids, depending on the nature of alkenes and the experimental condition in which our reaction is taking place. Let's see how is the alkene's structure important for the end product. So, what is happening in this reaction? Again, your double bond between carbon is breaking and both carbons are getting oxidized, means they are gaining oxygen atoms or they are losing hydrogen atoms. So, this is the key feature of any oxidation process. What is the product? How it will depend on the structure? Let's see. If your carbon has hydrogen atoms attached to it, then it will become a carboxylic acid. So here is an example for that. We are taking butene. So both of the doubly bonded carbon have 1 hydrogen each. If you react this with your KMnO4 in the presence of an acid, so acidic KMnO4 basically, in diluting condition, then it will result in 2 moles of ethanoic acid. Means both the bonds between carbon is broken, resulting in 2 fragments, and each fragment is oxidized enough to get your ethanoic acid. But suppose your carbon has no hydrogen atom. There is a case your carbon has no hydrogen atom. In that case, your alkene will be oxidized to ketone. So this was the oxidation reaction of alkenes. Now we will talk about the ozonolysis process. So what is ozonolysis? I have told you in the start that ozonolysis is the reaction of alkenes with ozone, which is O3, to form a compound known as ozonoid. A ozonoid is a ring-like structure that temporarily holds the atoms together. Before the next step, notice how the ozone adds across the double bond, splitting them apart. Next, we need to break down the ozonoid to get our final product. We do this by treating the ozonoid with zinc and water. This step splits your ozonoid and produces either aldehydes or ketones depending on the structure of original alkenes. Aldehydes and ketones are both type of carbonyl compound, which means they contain a carbon-oxygen double bond. So, ozonolysis is especially useful because it helps us to detect exactly where the double bond was in the original alkene by analyzing the product form. We can figure out the position of the double bond in the starting molecule. Let's see how. For example, in the step 1, what will happen? The alkene will react with ozone to form ozonoid. You can see in the reaction how the ozone molecule is getting attached to the double bond of the propene to form the propene ozonoid. That is the next step. This ozonoid which is formed is further reduced by the zinc and water to form what? It is forming your aldehyde, which is ethanol and methanol. So these are the products of your ozonoid breaking. Moving on further. Next we have polymerization process. So what is polymerization? Here the monomer, which is an alkene, adds to form a long chain polymer. Each monomer, which is an alkene, adds to the growing chain, creating a long repeating structure. The double bond in the alkenes open up and link together, forming strong covalent bond along the chain. This process can produce material with very different property depending on the monomer which is used. Right? For example, we are taking ethene molecule, which has the molecular formula CH2 double bond CH2. Now, under combined high temperature and pressure along with a catalyst, they form polyethene, also known as polythene. The reaction can be written as N moles of CH2 double bond CH2, leading to the formation of a polythene. So this N written in the subscript represent that your CH2 unit is being repeated N times. Notice how the double bond is broken and replaced by a single bond in the polymer chain. Now, polythene is used in polythene bags, bottles and wires. The properties of polythene, such as flexibility and strength, come from the way the polymer chains are arranged and how long they are. Finally, the polypropene, if we use in place of ethene, propene, it is used to make milk crates, buckets, plastic chairs, etc. Let us summarize our today's class. So we started with the physical properties of alkanes. It was seen that they are generally colorless or odorless. This means they don't have a strong smell or visible color, which is important when handling them in lab or industry. After that, the key property is that your alkenes are insoluble in water. This means they do not mix with water, much like oil. This property is due to their non-polar nature, which is a common trait among hydrocarbon. Right? Then we have electrophilic addition reaction. So let us look at the addition of hydrogen, also called hydrogenation. In this reaction, alkenes react with hydrogen gas in the presence of a nickel catalyst. The double bond breaks and the 2 hydrogen atoms add to the carbons, turning your alkene into alkane. Next, we have addition of halogen, such as bromine or chlorine. When these halogens react with an alkene, they add across the double bond to form what we call vicinal dihalide. where the two halogen atoms are attached to the adjacent carbon atoms. Then we have the reaction of alkenes with HBr or HCl. So they are hydrogen halides. So this reaction is called dehydrohalogenation reaction, and hydrogen and halogen add across the double bond. The way they add depends on the structure of alkene and the reaction condition. How? In Markovnikov addition, when HBr is reacting with the propene, the hydrogen atom attaches to that carbon with more number of hydrogen present already, and the bromine atom attaches to the carbon with fewer hydrogens. This produces 2-bromopropane as the major product. Next, we have the anti-Markovnikov condition, where we have a peroxide present in the reaction mixture. Here the bromine atom attached to that carbon with more number of hydrogen, contrary to that of the Markovnikov addition, resulting in the formation of 1-bromopropane as the major product. Moving on further, we have the addition of sulfuric acid. So the addition of sulfuric acid is also an example of electrophilic addition, and further it is done in the Markovnikov fashion. Means the alkyl hydrogen sulfonate act as an intermediate here, which is further dissociated to form the alcohol. Last is your hydration. So in this process, a few drops of concentrated sulfuric acid help in the catalysis of the addition of water onto the double bond to form alcohol. This also follows the Markovnikov process. What are the other reactions that we studied? The specific reaction. The first one is oxidation. So alkenes on reaction with potassium permanganate produces vicinal glycols, which is basically those dihydric alcohol where the two alcohol groups are present on adjacent carbon. Next, we have ozonolysis. So ozonolysis of alkenes involves the addition of ozone molecule to form ozonide, which is further broken by Zn and H2O to form the aldehyde and ketone, depending upon the nature of your double bond position, right? Lastly, we have polymerization process, where your single unit is combined to form a long chain. They can be done with the help of ethene to form polythene or propene to form polypropene, and these products are used in our daily life in weight products. Okay, so this was all for today's class. Thank you for joining the session. I hope you enjoyed it.